So what is Boolean logic? It's simply just manipulating ones and zeros or true and false or on and off, whatever you'd like to call it. It's basically manipulating signals, whether a signal passes or not. So if a signal passes, that is indicated by a 1. And if a signal does not pass, then it's indicated by a 0. So this very simple mechanism is exactly how we're going to be building the simple hardware devices that we have mentioned before. And the first step to make those devices is by analyzing Boolean functions. So what exactly is a Boolean function? In textbook terms, it's just something that takes input signals like X and Y and outputs an output signal. Now for a better understanding, you could think of it like a security guard. So it's basically some sort of a security guard or a bouncer that has a list, a specific list of people who pass and who do not pass. So for example, let's say that the list says that all guests have to wear a suit. So a suit. And they shouldn't wear a hat. No hat. We're going to indicate that X is equal to whether the guest is wearing a suit or not. And Y is going to indicate if he has a hat on or not. So what this function does is that it's going to only pass people who have X equals 1 and Y equals 0. So we could actually make a table that includes all of the possible values for X and Y, which is whether the guest has a suit on and if he has a hat on or not, and whether he gets in based on those inputs. So let's say that the user is not wearing a suit and he is not wearing a hat. Well, our function body specified that the user has to wear a suit and he should not wear a hat. So he is not wearing a hat, which is correct, but he's not wearing a suit, so he's not getting in. What about if the user is wearing a suit, but he does not have a hat on? That is exactly what we want, so he is getting in. But what if the user does not have a suit on? So 0 here. But he does have a hat on. That is the exact opposite of what we want. He is never getting in. And what if he has a suit on and a hat on? He is also never getting in. And this table that we have effectively created is basically what's called a truth table, which basically exhausts every single possible input into our function. So how does all of this relate to logic gates? Well, logic gates are just a representation of those functions. So this is the physical representation of the Nand gate. It takes X and Y and produces some output. You could basically consider this diagram as the bouncer or the security guard that we mentioned before. It only passes a signal when it matches the body of it or how it's wired on the inside. So if X and Y match the internal wiring inside the Nand gate, it will produce a 1 here. So let's talk about the AND gate. So what is the truth table of the AND gate? What is the logic to the AND gate? How does it handle the incoming signals to it? Well, it's actually pretty simple. It only passes the signal if both inputs are on or equal to 1 or both inputs are true. So basically the AND gate's output is only ever equal to 1 if both the inputs are equal to 1. So you can actually imagine how simple the truth table for the AND gate is going to be. So for 0 and 0, we're going to get 0. For 0 and 1, we're going to get 0. For 1 and 0, we're going to get 0. For 1 and 1, we're going to get 1. Super simple. And the AND gate has a really nice symbol, which is X dot Y, or just X, Y straight away. This means X and Y. X and Y. And here's the diagram for the AND gate. So next up is NOT. NOT is actually the simplest logic gate to ever exist. It takes the input and inverts it. So if X is equal to 0, the output is going to be 1. And if X is equal to 1, the output is going to be 0. Super simple. And again, to emphasize, this is the diagram for the NOT gate. It's basically a triangle with a dot. And how you represent NOT using symbols is the input variable as it is with a bar on top of it. and it reads X bar. Okay, so the next gate is OR, which is also called inclusive OR. We will mention that later, why it's called that. Inclusive OR. So OR is actually very generous. It almost lets anyone in except 0 and 0. So if there are no input signals, it outputs 0. Otherwise, everything else will give a 1 signal. So yeah, this is a truth table for OR. It basically lets all signals through except when both signals are turned off. And this is the symbol for the OR gate. Kind of like a spaceship. And this is the algebraic notation of OR. It's X plus Y. Yeah, the same plus symbol that you use in regular algebra. But here it means X or Y. Now for the start of this series, the NAND gate. So I would like you to pause the video and finish the NAND table yourself. A big hint is like what we said before, is that NAND stands for not and. Okay, so hopefully you got it. So and only gave us a signal when X and Y were both equal to 1. So NAND is literally just the opposite of that. So it's gonna give us 0 when both X and Y are equal to 1, and it's gonna give us 1 otherwise. And this is the diagram for NAND. It's basically the exact same as AND except for this dot right here, which is basically the N in NAND, which literally just stands for not, like we said. And this is the algebraic notation for NAND. It's X dot with a circle on it, Y, which reads X NAND Y. And there is actually a different way to write NAND. You could type X dot Y and take all of that into an inverter, and now you have NAND. This is basically X and Y, pass it through an inverter, which gives us not AND, which is NAND. This should give you an idea of what I mean. Okay, so NAND is actually quite special because it has a property that it can be used, like you can use a combination of multiple NAND gates to make other simple logic gates and build on top of those to build more complex logic gates. Okay, so something really funny happens. If we have a NAND gate and we take the first input wire and connect it to this variable X, and we also take the second variable wire and also connect it to X, something really funny happens. If we take a look at the truth table for the NAND gate, if we look at X and Y, we can basically eliminate this Y because it's the same input variable. It's just X and X. Which means that those two cases are basically impossible because the same signal is being passed to both wires. And by eliminating the second colon because it's useless, it's literally just the same variable. If we go ahead and look at the truth table back again, if X is 0, we get 1. If X is 1, we get 0. So 0, 1, 1, 0. So if you have a keen eye, this is literally just a NOT gate. So if you take a NAND gate and connect the same signal to both of the input signals inside the NAND gate, you have effectively created the NOT gate from NAND. So if we were asked to create a NOT gate from a NAND gate, it's actually really simple. We'll create a simple box like this. We have an input pin outside of it. We'll call this X. We will call this out. And we will have a single NAND gate inside. Connect the output and connect the first wire, the first input wire to X and the second input wire to X. And we're gonna call this NOT. And this is basically what we're gonna be doing. We're gonna be creating more gates like this one from just NAND and the gates that we're gonna be creating on top of NAND. So now that we have created NOT, we could consider a virtual toolkit that we have, which consists of an infinite number of NAND gates and NOT gates, because we have already created NOT using a single NAND gate. Now our next task is to create an AND gate from the gates that we have in our toolkit. Please pause the video and try this yourself. Okay, hopefully you got it. It's actually really simple. NAND is literally just NOT AND. So what if you NOT AND? Well, Both of these cancel each other out, and you have AND. So if we were to create a black box that has two input terminals, X and Y, and we have a NAND gate inside, we connect X to the first input terminal of the NAND gate and Y to the second input terminal of the NAND gate, and we connect the output of the NAND gate to an inverter, we have effectively created the AND gate. And now we could consider our virtual toolkit again to have an infinite number of AND gates, an infinite number of NAND gates, and an infinite number of NOT gates. So now our third task will be to create the OR gate from this toolkit. Here is the truth table for the OR gate. Please pause the video and try to do it yourself. And note that this is a little bit tricky, and you may not get it right away, and that's okay. Okay, so don't worry if you did not get it right. This is a little bit more involved. Let's look at the truth table for the NAND gate. If you notice, it is the exact same as the OR gate, except that the 0 and 0 case and the 1 and 1 case are inverted. So basically all we need to do is somehow switch both of these cases up, and we're gonna have an OR gate. So how could we possibly do that? The answer is pretty simple. So if we have our two inputs, X and Y, and we know we're going to use a NAND gate, and we need to switch the 0 and 0 case, maybe we could try something like this. Where we basically connect an inverter to both of the input signals, and this will give us our OR gate. Okay, so let's look at the truth table for this schematic. So for the 0 and 0 case, both of them get inverted. So we're passing 0 into Y and we're passing 0 into X, which both of them get inverted into 1 and 1. 1 and 1 is the only case in a NAND gate where it outputs 0. So we get 0. So the 0 and 0 case is going to be 0. So what about the 0 case in X and the 1 case in Y? So let's try it. 0 and 1. 0 gets inverted in X, so it becomes 1, and 1 gets inverted in Y, which becomes 0. 0 and Y in a NAND gate is 1, which gives us 1. What about 1 and 0? Again, same case. This gets inverted, becomes 1. This gets inverted, becomes 0. 1 and 0 in an AND gate gives us 1. So another 1. What about the 1 and 1 case? Again, both of them get inverted into 0, 0. 0 and 0 in an AND gate gives us 1. And we have effectively created the OR gate. Okay, so why does this work? Well, the answer is quite simple. If you look at the NAND gate, basically, like we said, it's a security guard or a filter or whatever analogy you would like to use. It only passes the 0 and 0 case and the 0 and 1 case and the 1 and 0 case, but it does not pass the 1 and 1. So what we have effectively done is we have swapped both of these cases by using an inverter. And these two cases, since they have the same output, it actually does not matter if you invert both of the inputs. This is an advantage of using only 1s and 0s as your input values. So basically why this works is that you have effectively just swapped the 0 and 0 case with the 1 and 1 case. Okay, so really quick and easy gate is the NOR gate, which is just not OR. This is super simple. You can pause the video and try it if you want. And as you have probably guessed, this is super simple. You just take an OR gate and you invert it. Okay, so the final gate for this episode is the XOR gate, which has the algebraic notation X with a plus and a circle on it, Y. And this is the gate symbol for it. So basically it's the exact same as OR, except it has this half circle before it. So what is the truth table for the XOR gate, and why did I leave it to the end? Now, XOR actually stands for exclusive OR. So what does that mean? Well, from OR, we can infer that it probably is quite similar to the OR gate, and it's in fact the exact same, except for one detail. The one-on-one case returns 0. So XOR basically only passes a signal when X and Y are different. So if X is 0 and Y is 1, we get a 1, or vice versa. Now for the final task of this episode, I would like you to implement the XOR gate from the gates that we have made up so far. And as a reminder, our toolkit now includes an infinite number of AND gates, OR gates, NOR gates, NOT gates, and NAND gates. You can use any of them however way you want to create XOR, which has this truth table. You can pause the video and try it out yourself. So don't worry if you did not get it. This one is a little bit more involved. So to effectively create an XOR gate, we only pass a signal if X is 0 and Y is 1, or when X is 1 and Y is 0. So XOR only passes a signal when X and Y oppose each other. So we only want to pass these two cases. Well, I have an idea. We know that the AND gate only passes a signal when X is 1 and Y is 1. Then our output becomes 1. If we have X and Y, and we take a wire from Y and invert it, and take a wire from X, but leave it as it is, and connect it into an AND gate, then the only case where the signal passes from both of these gates is when Y is 0 and X is 1, effectively giving us the first case. So the only time that a signal passes is when Y is 0 and X is 1, because X gets passed as it is, which gives us 1, Y gets inverted and becomes also a 1, 1 and 1 into an AND gate is 1, which is basically one of the cases that we want, and all of the other cases are ignored. Okay, that makes sense, but what about the other case? We're actually just gonna do the exact same thing. We're gonna get another wire from Y, but we're not gonna invert it, and we're gonna take another wire from X, and we're gonna invert it, and pass both of them into another AND gate. And this case is gonna give us, if Y is 1 and X is 0, the X gets inverted and becomes a 1, and this AND gate. So now we have a problem. We have two output wires, but XOR has a single output wire. So how do we fix this issue? Well, I know that the first set of gates has only a single case where it's gonna pass a value, which is when Y is equal to 0 and X is equal to 1. And the other set of gates also has the same logic, except it's inverted. So we can basically just connect them using an OR gate. Because the two AND gates have opposite conditions, it's physically impossible for both to output a 1 at the same time, because one is looking for X and the other one is looking for not X. So by plugging both of them into an OR gate, we're essentially saying, give me a signal if scenario A or scenario B is true. Because they can never happen at the same time, we are using the OR gate to merge two paths that will never collide. Okay, so let's start with the first case, where X is 0 and Y is 0. So X is 0 and Y is 0. So in the first set of gates, Y gets inverted and becomes 1, and X goes as it is, which is 0. 1 and 0 in AND is 0. Now for the second set of gates, X is 0, which gets inverted and becomes 1, Y is 0 and gets passed as it is and becomes 0. So 1 and 0 into an AND gate, which is 0, 0 and 0 into an OR gate, which gives us 0. Okay, so the first case is 0. Perfect. So Y gets inverted, becomes 0. X remains as it is, which is 0, 0 and 0 into an AND gate, which is 0. Now in the second set of gates, X gets inverted, becomes a 1. Y gets passed as it is, which is 1. 1 and 1 into an AND gate, which gives us 1. 0 and 1 into an XOR gate, which gives us 1. Okay, so far so good. We got our first result that we want. Okay, so now for the 1 and 0 cases. So x is 1 and y is 0. Okay, so y gets inverted, becomes a 1. X remains as it is, which is 1. 1 and 1 is 1. Now for the second set of gates, x gets inverted, becomes a 0. Y is 0. 0 and 0 to an AND gate, which is 0. 1 or 0, which gives us 1. So again, the second result that we want. Now the final result should give us 0. Let's check that out. Okay, so the 1 and 1 case. So y gets inverted, becomes a 0, but x is 1, so 0 and 1 into an AND gate, which is 0. For the second set of gates, x gets inverted, becomes a 0, y is 1, 1 and 0 into an AND gate, which gives us 0, 0 or 0 gives us 0. So the final result is 0. Don't worry if you didn't get this one on your own. It's a little bit more involved, like I said. Okay, so as an added bonus challenge, if we take a look at our XOR implementation, we can see that we have used 5 gates. But there is actually an optimization that you can make. So the challenge is to use 4 gates to make XOR. And here's a cheeky little hint that may help you. Do not use AI or look it up on Google unless you are unable to solve it on your own. The next video is going to cover Boolean algebra properties. We're going to be actually showing the notation for each of the gates and solving it like regular algebra. We're going to be also explaining hardware descriptive languages, and we're going to be using the Nand2Tetris IDE to actually simulate the gates that we have made today. So yeah, it's going to be quite exciting, I guess. And I would have done it in this video, but this video is already long enough. I don't think anyone is even going to watch it to the end, but yeah, I had fun at least.